This video provides a demo of the DynAlloy Analyzer tool, a tool for the specification and analysis of alloy models with dynamic behavior. As a sample model, we will use the cross-river puzzle, the well-known problem of finding a way for a farmer to cross a river with a chicken, a fox, and a sack of grain, avoiding losing items in the process. We chose this model because there is an alloy model for it available in the set of sample models of the Alloy Analyzer tool, and it is a case that demands dealing with dynamic behavior. The original alloy model features an explicit characterization of state traces using total orders on states, and comes with predicates whose satisfying instances are solutions to the puzzle, as well as with some properties to be verified, like for instance that no item can be on both sides of the river at the same time. Now, moving to our DynAlloy language, we avoid the explicit characterization of traces via the definition of atomic actions for basic transitions and the construction of composite programs that involve assumptions whose executions correspond to puzzle solutions. For commands that lead to satisfying instances, as the solve puzzle case, DynAlloy Analyzer provides a visualization that allows us to explore the execution traces. On the right-hand side, we have the trace, and as we proceed on it, we can track the parts of the model being exercised, similar to the way a debugger would work. Moreover, we can explore the actual state at each step, simply unfolding the corresponding step and checking its pre- and post states. For our particular example, we can see that we start with all objects on the near side of the river, while in the last state we effectively have that all items have reached the far side of the river. We can also boundly verify properties regarding executions. Some sample properties are no quantum objects, that is, that no object can be on both sides of the river. Another one states that the farmer is always there, that is, no transition loses the farmer. And finally, one property that states that if an object is lost along an execution, then there is no way we can resurrect that particular object. Just to illustrate the expressiveness of DynAlloy, let us reconsider the atomic action for crossing the river. We can redefine this atomic action as a composite one that, provided that the farmer is on the source side of the river, that is the side from which we are going to start the crossing, it successively chooses one item on that side, it removes the farmer and the item from the source side, then updates the source side losing the objects that are eaten by other objects on the same side, since they are now unsupervised, and finally takes the farmer and the selected item to the destination side of the river. We can also analyze this program looking for puzzle solutions. The Alloy Analyzer instance visualization is also available in DynAlloy Analyzer. We have, of course, in this model more intermediate states now, since the atomic action for crossing the river is now captured through a program. We can analyze, for instance, how each state is composed using this visualization. For example, checking that the initial state and the final states are as we expect them to be. Further information on the use of DynAlloy Analyzer, as well as the binaries of the tool and sample models, can be found in the following website.